Alright class, today we're going to be talking about section 2.6, which is on continuity. Now that we have limits, we can actually get a good definition of continuous functions. I mean, the one you've probably heard before in algebra or pre-cal. It's always been this sort of like hand wavy, like I could draw the graph without lifting my pen kind of stuff. That's not a very good definition. There are a lot of problems with that. So here is the actual definition. Okay, is that a function is continuous, okay, at a point, say at a x value a, if and only if the limit as x goes to a of f of x is equal to f of a. Okay, couple things to note here. The first thing is that this is a pointwise property, or a pointwise definition. That means continuity is not a general, a graph is continuous or it's not. It happens at a point. Okay, is the function continuous at a, for example. And continuity basically boils down to whether the function value and the limit match there, right? So basically a function is continuous if the function value and the limit match, okay, i.e. the function value, which is what I like to say for f of a, matches the limit. Okay. Now, if a function is continuous on an entire set, okay, so if a function is continuous for all x in a set a, b, like an interval a to b, then we say f of x is continuous on that set. So that's when I say a function is continuous on, say, 0 to 1, this could be an open set or whatnot, that just means it's continuous for every point in that set. Okay. So let's look at an example. Let's maybe take a look at a graphical example. That's a good thing to start with. Say here, just from the things you've known before about functions, we know that the function is not continuous here at this little open dot, right? By the old definition we have, we know it's because, well, I can't draw this without lifting my pen. I have to jump over this open dot. Okay? But the real reason that the function is not continuous at 2, okay, remember it's a pointwise thing, at 2, is mainly because the limit exists, right? If I look at the limit on both sides, we see that the points I draw get closer and closer to this open dot. Right, so the limit of this function, which I'm going to call x, f as x goes to 2, is actually equal to 3. Okay, but what is f of 2? Well, I have no f of 2. There's a hole there. So as we've seen in some of our worksheets, this means that f of 2 is undefined. Now, does 3 equal undefined? Of course not. So f is not continuous, okay, at x equals 2, since the limit as x goes to 2 of f of x does not equal f of 2. Okay, they don't match, so the function can't be continuous there. Okay, let's look at another example. This one might look a little familiar. We used it in a previous lecture, but that's okay. So I'm going to look at -2 to begin with. Right. X equal to -2, so that's here. Let me switch this out real quick. Okay. And it's clear that here the function is not continuous. I mean, there's an open dot, there's a hole, it jumps down to this point, jumps back up, and continues on. Clearly not continuous. I cannot draw this, without lifting my pencil. And like I said before, that's not even a very good way to talk about these things, right? So let's take a look at what's going on. We'll call this function g. Okay, so what's the limit as x goes to -2 of g? And we've had enough practice with that now that you probably see that that is actually 3. Right? The limit is 3 because that's what the function's getting closer and closer to as x gets closer and closer to -2. But what is g of -2? Now when x actually equals -2, we go to where the closed dot is, and that's down here at -3. Okay. Do these two guys match? Absolutely not, right? So g is not continuous. If you can read that, at x equals -2, since the limit as x goes to -2 of g of x does not equal g of -2. Right? This is what you're expected to write. I mean, most of these problems are going to ask you to explain why it's not continuous, why it is continuous, and this is what you're going to put, right? That the limit and the function value do not match. They're not equal. Okay, next up let's try looking at -1. When x is equal to -1, okay, it's pretty clear that the function's not continuous there, right? We go along here and then we have to jump down to here, right? We have to lift our pencil. This is what is called a jump discontinuity. All right, this guy up here, this is what we call a removable discontinuity. You don't necessarily have to know these words, but this is a removable discontinuity because, well, the limit exists, but it doesn't match the function value. And you can think of it, it's called removable because what do? We just take this point that used to be here and move it down here. Or with this example that we looked at previously, we just remove the point completely. Right? That's a removable discontinuity. On the other hand, this one is called a jump discontinuity, which should make sense. We're jumping, right? The function jumps. It's not continuous. It doesn't stay connected the entire time. There's a jump. Okay? And a jump discontinuity, well, would you say that the limit exists here at -1? Well, I would say absolutely not, right? Because the limit from the left is going to 2, and the limit from the right is going to 0. Okay? So the limit, the two-sided limit, as x goes to -1 of g of x simply does not exist. Pure and simple, does not exist. So it can't equal the function value, right? The function value is 0, right? G of -1 is 0. If we go here and look, that's where our closed dot is. That definitely doesn't equal, does not exist. So what we will say is that g is not continuous, okay, at x equals -1, since the limit as x goes to -1 of g of x does not exist, right? That's all you need to have, something be not continuous, right? The limit does not exist. If the limit doesn't exist, that means, well, you've got to jump, right? That's typically what it means, that the left side and the right side don't match. That's definitely not continuous. Okay. Finally, let's look here at, say, 2. Okay, when x equals 2. Okay, so we see, just from what we know, that this is continuous, but let's talk about limits in this case. All right, so let's start with looking at the limit as x goes to 2 of g of x. And we see that on both sides, the graph is getting closer and closer to, if I map over here, negative 1. And then g of 2 is also, I map down, there's a closed dot there, also equal to negative 1. Since these guys match, right, we can say that g is continuous at x equals 2, since the limit as x goes to 2, g of x is equal to g of 2. Okay. So those are like our three cases. Basically, we got down to a function is continuous if the limit and the function value match. So we finally have a case where they match. Okay, you can pretty much stop this process once one of them does not exist. Okay, so that brings us to what we call, or the book calls, the continuity checklist. Okay, so here's the continuity checklist. Right, so say we want to check, is f of x continuous at x equals a? Okay, is this function continuous? Well, we go through this checklist and we have this order for a reason, because it's basically the easiest way to go about it. All right, 1, does f of a exist? Okay. If you try and plug in a, if you try and plug in the value and you get undefined, you get the function is undefined there, you're done. Stop. The function is not continuous. Okay, you can stop right there. Okay. And the reason that one comes first, that's the easiest one to check. Since number 2, does the limit as x goes to a of f of x exist? Well, that's a little tougher to check, right? Because typically what you have to do to check that is check both sides, right? The left-hand limit, the right-hand limit, see that they match. If those two match, that means the limit as x goes to a of f of x exists. Okay? If the limit doesn't exist, you're done, right? If the limit doesn't exist, the function is not continuous at that point. Okay? And then 3, do they match? Does the limit as x go to a of f of x equal f of a? Do they match? If they match, the function's continuous. If they don't, then it's not continuous. So all 3 of these must be satisfied for f to be continuous at a. Okay? You have to have all 3 answers there be yes. If any one of them is no, the function is not continuous there. Okay, so the nice thing about this order is I can pretty much say, hey, is f of x equal to 1 over x continuous at x equals 0? And I can say no immediately. Why? Because f of 0 is undefined. Bam, done. Okay? Is f of x equal to 1 over x continuous at x equals 0? Absolutely not. Okay? F of 0 is undefined. And in fact, if we go back to the graph of 1 over x, here's the graph of 1 over x here, you see we get a blow-up point at 0. And from the right, the function's going to positive infinity. From the left, the function's going to negative infinity. Okay, and the function has no value at 0. So not only is it undefined at 0, we also have the limit doesn't exist. And that's the same for 1 over x squared, that blow-up point, even though the limit is infinity, which, keep in mind, is still a type of does not exist. There's nothing here on this line. Right? At 0, 1 over x squared is still undefined. So that's why that part of the checklist comes first, because if you can't plug the value in and get an actual number out, you're pretty much done. The function is not continuous there. Okay, so let's start looking at some more complicated examples. This first one is a piecewise function, and I'll say that piecewise functions are one of your most commonly used examples to talk about continuity analytically. I mean, you have graphs, that's one way to do it, and then you have your functions, and a lot of functions that you can just write out, just by hand. Typically, like as an f of x equals something, typically are continuous, for the most part. Now, one thing. So, sorry, lost my train of thought there. But piecewise functions, on the other hand, are broken up into pieces, and wherever those pieces join together is a prime example or prime suspect for a place where you might have a jump discontinuity, for example, right? Because, well, there's the possibility that these pieces of these functions don't join together. So often the book will say, or your online homework will say, hey, check the continuity here at 3. Or they'll just say, hey, where's this function not continuous? Now, this 3x plus 1, that's pretty much continuous everywhere, as is 1 minus x, right? Polynomials are nice and continuous everywhere. The thing you've got to worry about is here at this breakpoint. So even if you're not told where to check continuity at, if you have a piecewise function, you basically want to check it at these breakpoints. Okay? So we're going to go through the checklist, right? And I'll go ahead and write, is f continuous at x equals 3? Right? So the first one, does f of 3 exist? Well, let's check f of 3. So f of 3, well, f of 3, that's when x equals 3, so that's going to be this greater than or equal to piece. So this will be 1 minus 3, which is negative 2. Okay, so yeah, it does, right? F of 3 exists just fine, no worries. Now we need to check to see, does the limit exist? So does the limit as x goes to 3 of f of x exist? That's our next question. Okay. So to do that, to answer that, we need to check both sides. All right, so I'll start with the side we already know. From the right, that's when x is greater than or equal to 3. This is going to be 1 minus 3, again, negative 2. We've already done that. And now I'm going to check it from the left. So that's going to be the top piece. Right, so I'm going to pick that top piece. And remember, always write at least enough so everyone knows what you're doing. I'm picking this piece. It's fairly clear now which piece it is. So that's 9 plus 1, which will be 10. And here's the question. Do these two guys match? No. So does the limit as x goes to 3 of f of x exist? The answer is no. Okay. And so, is f of x continuous at x equals 3? The answer is no. And you're always going to be asked, for the most part, to write why. And the answer is because the limit as x goes to 3 of f of x does not exist. Okay, so here's our next example. Let's take a look at the continuity of this particular function. Now, this one looks really bad to start with, but we're going to pretty much be able to finish it pretty quickly. We have that g of x is equal to x to the 100th minus 65x squared minus the square root of 33x for when x is greater than 0. And 17x to the 13th minus 45x to the 7th plus 33 when x is strictly less than 0. So the question is, g of x continuous at x equals 0. And the reason I only have to worry about 0 is mainly because, well, this function, we have a square root, but everything else will be continuous everywhere, and since we're only looking at positive x's, this thing is fine. And then this piece is a polynomial, so that should be continuous everywhere. The only piece, or the only thing we have to worry about is those endpoints, or these breakpoints, I mean. Okay, so that's what we're going to check, is g of x continuous at 0? And the answer is no, because the first thing in our checklist is, does g of 0 exist? And the answer is no. Okay, so is g of x continuous at x equals 0? Nope. Okay, and the reason is, since g of 0 does not exist, or g of 0 is undefined. Right, we already wrote that here, but typically this is, you're just going through this, you know, on your own. But basically, since g of 0 does not exist, g of x is not continuous at 0. Right? So, and that's, just as a reminder, that's because we don't have an or equal sign anywhere. Okay? So if you don't have an or equal sign, that piecewise function is not going to be continuous like that. You're done, you move on. Okay, so for the next example, let's look at f of x is equal to x squared plus 1 when x is less than or equal to 1, and the square root of 2x plus 2 when x is strictly greater than 1. Okay, now which point are we going to be looking at? X equals 1, of course. Right, so is f of x continuous at x equals 1? Okay. So what's the first thing we look for? Does f of 1 exist? Okay. So we have an or equal to sign, so yes, it will be 1 squared plus 1, right? We go to this top piece because that's when x is equal to 1, and so we get to 2. Okay. Next thing is, does the limit exist? So the limit, well, we've got to check both sides. So I'll start with the piece we already know. Right, the limit as x goes to 1 from the negative side, so that's the top piece. And so that's going to be 1 squared plus 1. Pretty much one of these pieces is going to, well, I shouldn't say that. If you have 3 pieces, so let me not say that. But in this case, this piece is going to work out. X going to 1 from the negative side, that's when x is less than 1, so that will be this piece. And then the next piece is going to be from the right, so that's when x is greater than 1, so that will be this piece. So I'm going to go ahead and plug my 1 into that. Right, and so that will be the square root of 2 plus 2, so the square root of 4, which is equal to 2. And oh, these two guys match. Right? So that means that the limit from both sides of f of x exists and is equal to 2. So we've satisfied that condition and that condition. And now, what's the final condition? Well, the final condition is that the limit and the function value must match. And do they? Well, yes, we got a 2 here, we got a 2 here. So, is f of x continuous at x equals 1? Yes, finally, we get a yes. And that's because the limit as x goes to 1 of f of x is equal to f of 1. They match. They're both, and you can say that they're both equal to 2 if you want, or however you write this, but this is usually the quickest way to write it. The limit as x goes to 1 of f of x is equal to 1. So the function is continuous at 1. Okay? And we had to go through all parts, right? We had to make sure the function existed, that the limit existed, so we had to check both sides, and that they matched. So keep in mind, it's very different things going on here. We have the left and right sided limits. If they match, the two-sided limit exists. Now if the two-sided limit exists and matches the function value, then the function is continuous there. Okay? That's the order it goes in. Okay, so this is basically the process. If you have the left-hand limit matches the right-hand limit, then that means that the limit exists. This doesn't mean that the function is continuous. Okay? It's only continuous if, okay, we see that the limit exists and it matches the function value which exists. Okay, and maybe I should add a function value exists all by itself, but basically the function value exists, we could say here, and it matches the limit which exists, then we get continuity. We get that the function is continuous. Okay, it's a big mistake to say that, oh, I checked both sides, they match, the limit exists, it's continuous. Absolutely not. You've got to have that the limit matches the function value. Now, with that said, what about functions that only exist on one side? Right? Say, if you'll pardon my by hand sketching here, but the square root of x, right? It starts at 0 and heads on that way, and it's got no values over here. Okay, so here the limit as x goes to 0 from the right of the square root of x, that exists, right? If you come at this side, it's 0, and that actually equals the square root of 0. But the limit as x goes to -1 of the square root of x doesn't actually exist because there's nothing over here, right? There's no graph. So that actually means that the limit as x goes to 0 from both sides does not exist. Okay. Yeah, kind of crazy, right? That this is a function that is continuous on its entire domain, but if we're considering everything here, we can't really say it's continuous at 0 with this definition. So what we actually say is that the square root of x is continuous from the right. Okay. Continuous from the right. Coming from the right, it's continuous. The limit and the function value match, and we can't say it's from the left because there's nothing, going on the left, right? So it's almost like all we're doing is considering the function here instead of everywhere. Okay, so keep that in mind, that for some crazier functions, you'll have continuity just from the right or just from the left at various places. But say at 1, the function will be just straight up normal continuous, two-sided continuous, right? Since the limit and the function exist there. Okay, here's some properties of continuous functions, right? We have some properties of limits, logs, all that kind of stuff. And these you've probably seen before. Basically, if f and g are continuous at x equals a, then f plus g is continuous at a, f times g is continuous at a, c times f, where c is a constant, that's continuous at a, f of x over g of x will be continuous at a, provided g of a is not equal to 0, right? That's always in your properties. You'll see just everything's not allowed to be or you're not allowed to divide by 0. Okay, and then f of x raised to the n power is continuous at a. All these are continuous at a. Okay, so sums, products, quotients, and this one here, this property is quite interesting because it actually allows us to do a lot of crazy limits that we might not have thought about. And you probably already got a sense of this in some of the things you worked on. But basically, if g of x is continuous at a, and f of x is continuous at g of a, then f of g of x is continuous at x equals a. And if all this stuff is true, what this basically means that if everything's nice and continuous where we need it to be and where we want it to be around a and all that, and note f has to be continuous at g of a because that's what we're plugging into f. If all this is true, then if I'm taking the limit as x goes to a of f of g of x, I can actually move it inside and take the f of the limit as x goes to a of g of x. And if everything's nice and continuous, we know that this is going to be f of g of a. Okay. So this actually can help with some crazy examples like the following. So say I want to take the limit as x goes to 2 of e to the square root of x cubed plus 1. Now, first thing we need to figure out, is this thing going to be continuous at 2 before I start just plugging and chugging, right? And it should be, right? E to the x is continuous everywhere, that's fine. Square roots are continuous provided everything's positive underneath. And we're looking at 2 here, and 2 cubed will be positive. This should all be positive underneath, so that should actually be fine. So we can go ahead and write this as e to the limit as x goes to 2 of the square root of x cubed plus 1. And this will be continuous, so we can actually move it within the square root to get e to the square root of the limit as x goes to 2 of x cubed plus 1. And from here, well, now we can just plug in 2, right? So this will be e to the square root of, that will be 2 cubed plus 1, and we plug that in. So that will be e to the square root of 9, so e cubed. Now, check this out. We have 2 here. We could have just plugged 2 straight in right here, right? Skipped all these steps and gone straight to here, and typically we can. The only thing you need to do is just take a moment to check to see whether that thing is continuous or not. Okay, and so this property we've just talked about is actually very helpful because now it brings us past just raising things to powers, right? Now it could be I'm taking the limit of sine of a bunch of junk, and sine is continuous everywhere, and what's in here, that's just a polynomial, basically. That's going to be continuous everywhere, so I can actually just move the limit inside of sine, since it's continuous. And this is only true if everything's nice and continuous, right? So, and the limit of this stuff, well, we're just going to plug in our 0 on the inside of sine there, so we'll get sine of 3 times 0 squared minus 2 times 0 plus pi over 2. Now, granted, you probably wouldn't write this all out like this. I mean, the zeros are just going to cancel. So this is sine of pi over 2, which we know is 1. Okay? There we go. These continuity limit properties let us move limits inside just about anything. Powers, e, log, sine, cosine, whatever, provided everything's continuous where we're looking at. Okay, so the last thing I really want to talk about in this section is called the intermediate value theorem. And this is just a really nice property about continuous functions that it's really important in the development of calculus, and just a nice kind of abstract idea to talk about and think about. Basically, it says that, let's suppose that f is continuous on the function a to b, or excuse me, on the interval a to b. Okay. Let's say L is a number between f of a and f of b, right? So the endpoints of that function. Then there is at least one number c in the open interval a to b where f of c is equal to L. Now, what is this saying? Basically, say we have a continuous function from a to b. Right? Now here's let's say the starting point, and here's the ending point. And let's pick a value L. Okay? Since this function is continuous, there must be an x value between a and b such that f of c is equal to this y value, right? Because here's f of a, here's f of b, right? And if I go over, there has to be an x that satisfies this. Say it's here. And it looks like there's another one like here. Right? So there has to be there must be a c where f of c, and this is between, I should say, between a and b, where f of c is equal to L, right? Has to happen. Another way to actually talk about this is, and this is the way I like, say the function's continuous, we have its starting point A, its ending point B, and we know it's continuous on this interval. And we know that this is f of A, and this is f of B. Now, it is impossible, right? It's impossible to draw a continuous function between this point and this point without hitting every single point within here, right? Without getting every point in this region between f of a and f of b. You have to hit every y value, that is. Okay? Every y value you will cross between f of a and f of b. You have to. There's no way to do it otherwise. Of course, the obvious way is just to connect them, and you will hit every point in the spectrum. But even if you tried to avoid it, like you came down here, but eventually you have to bring your graph back up here to b, and you will hit every y value between f of a and f of b. The only way you can't do it, or the only way it won't happen, is if you made a function that was not continuous. Say you did down to here, and then right to here. Okay? The only way to do it without crossing all those y values is with a jump discontinuity. Okay? That's pretty much it. Right? So that's what the intermediate value theorem is all about. Basically, it just says that if you've got a continuous function, it's going to cross through all the y values between f of a and f of b, right? Between all the y's of your endpoints. And possibly more, but definitely all of those, right? It has to cross all of those, maybe more, okay, but not less. All right, and that's pretty much all there is to talk about with continuous functions. So I'll talk to you all next time. Cheers.